Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. So in the last 2 weeks, we introduced the basic concepts of EM waves. We talked about dispersion, diffraction limit and so on. And then we talked about the optical properties of materials, metals, dielectrics, how they behave. We derived the Lorentz oscillator model and the Drude model, which is an extension of Lorentz oscillator model. So in this week, I want to talk about optical properties of low dimensional systems. So what do I mean by low dimensional systems? Well, if you look at the bulk materials, there are three-dimensional materials. Electrons can freely move about in all the 3 dimensions, and so we call them the 3D or bulk materials. But suppose if I somehow confine the electrons to move only in a certain plane. For example, here I am showing you a quantum well. A quantum well essentially confines electrons to move about only in the plane. For example, if I call this as my x-axis. So, and let's say the thickness of this strip or, is 10 nanometers, let's say, just for the sake of example. If I confine my electrons to move about only in the 10 nanometer dimension and anywhere on the, if I call this as X and YZ plane can be anything. This is my Y and Z. It can freely move about in the YZ axis, but only in the X axis it's confined to about a 10 nanometer length. That is my quantum well, right? Similarly, I can also think about 2-dimensional confinement. So I can let the electrons move about in the Z axis freely, but confine them in the XY plane, confined in XY plane. So I'll call it as a nano wire. Okay. And then I can extend it even further. I can confine an electron to move about only in the, confine it in all 3 dimensions, and that will give me a quantum dot, as shown in the right picture here. So these are essentially lower dimensional structures. A bulk structure is 3D, the regular one. 2D is 1-dimensional confinement. 1D nanowire is a 2-dimensional confinement. A quantum dot is a 3-dimensional confinement. Essentially, this diameter of this dot could be something like 10 nanometers. Okay. So this is a confined structure. And it turns out that, so far in the last week, we have seen the material properties, but we never really took the size of the structure into account. Okay. So this is an extension. So what happens if you have such structures? How do the optical properties change? Okay. Let's consider first the metals. That's where we left off last week. So let's look at metals. Okay. Metals are described by Drude model. We have already talked about it. Let's say epsilon omega equal to epsilon infinity minus omega p square divided by omega square plus I gamma omega. This is my Drude model. So what happens? This is valid for, let's say, a bulk piece of metal. A couple of centimeters of metal is there. This will work. But what if I try to confine it to a quantum well? I just make a metal film of, let's say, 20 nanometers. What will happen to the optical properties? Well, it turns out that if you have metals, you don't need to really worry about the low dimensional confinement properties. Okay, unless you go below, let's say, 2 nanometers or 2 to 3 nanometers of size, you don't have to worry. Okay, the metal behaves similar to a regular bulk metal, but the moment you make a thin film of metal of 2 nanometers, the dielectric function itself changes and it acquires basically a character. From epsilon omega, you have to start talking about epsilon of k comma omega, where k is my spatial frequency. 2 pi by, let's say, confinement is happening in the size is basically d, okay, the thickness of the film. Let's say in that case we can assign a spatial frequency 2 pi by d, and then you have to take that into account and it becomes slightly complicated. But anyway, overall confinement doesn't really matter. Okay, confinement effects do not or rather are not significant for sizes greater than, let's say, 3 nanometers. Okay, so we don't have to worry about most of the time, and in this course we really don't want to get into that. Okay, but what we will study is the semiconductors. If you look at semiconductors, the confinement effects are significant. Okay, so for example, if I make a semiconductor out of a 10 nanometer wide semiconductor, let's say quantum well, okay, it plays a significant role. So confinement effects are significant. All right. So how significant? Significant. Why should we care about confinement effects? So the question is, why are low dimensional systems important? Okay. So I'm giving you examples here. So the image on the left, you see what is known as high resolution transmission electron micrograph, TEM image. So what this is showing you is a layer of aluminum arsenide sandwiched between two gallium arsenide layers. So this is my gallium arsenide, right? And the bottom is another gallium arsenide here. In between them, you have a aluminum arsenide. The beauty is, if you look at the axis here, this is 1 nanometer. So effectively what you're looking at is this part of aluminum arsenide is only 2 nanometers. And you can actually count here, let's say 1, 2, 3, 4, 5 and 6 atomic layers. So what you are seeing here is the atoms of aluminum and arsenic. Okay. And in the bottom and the top, you're seeing gallium and arsenic. And that is why you see this, the sizes of the dots are larger in gallium arsenide, because gallium is a much larger material, whereas aluminum is a smaller material. So the dots are smaller as well. So you clearly see that effect. Okay. So now what happens is, if you have such a structure, what would happen? Okay. So this is an example of a confined structure, because in this case, okay, if you look at aluminum arsenide, well, aluminum arsenide has a band gap of about 2.1 or 2.2 EV, 2.1 EV, let's say. And then gallium arsenide has a band gap of 1.42 EV. So I'm able to basically make structures with different band gaps in this sort of a supercell. Okay. Why is this important? Well, I have an example here on the right, which is taken from a textbook Niemann. So what you see here is a gallium arsenide structure sandwiched between aluminum gallium arsenide. Okay. So I told you that aluminum arsenide has a band gap of 2.1 EV, but by varying the composition of aluminum and gallium, we can achieve different amounts of band gaps slightly. And what you see here is a low EG material. Band gap of gallium arsenide is 1.4 EV, and aluminum gallium arsenide will be high EG band. Okay. So we are sandwiching a low band gap material between two high band gap materials, and this structure can be as small as 2 nanometers. It can be typically about 10 nanometers size. What happens if you have such a structure? In that case, what happens is you can actually create both electrons and holes to be in the same physical region of space. So for example, here I can try to introduce my electrons from the left side and holes from the right side into the same region, which has a smaller band gap. So electrons and holes will go and accumulate there, and then they can recombine and actually give you light. Light emission can happen. And it turns out that this sort of a low dimensional systems, we call them as quantum wells. They are very, very important for light emission applications. So let's say whether you look at, let's say, an LED or a laser and so on, they are very much dependent on this technology. Okay. An example is shown on the bottom here, wherein instead of just 2 layers or 3 layers, we have a stack of multi-layers of quantum wells, and then in between you have an active layer here in the center. Active layer means it actually emits light, and surrounding that you have basically an interface, a super lattice of various refractive indices that will actually work as a mirror, and it forms a nice laser cavity. We'll talk about lasers in the week 7 or 8 of this course, but for now what happens is you have this and the light emission happens. So this sort of low dimension systems are very important for lighting applications or lasers. Lasers are essential for all the communications. For example, if you don't have a proper laser at 1.5 microns, you don't have any of this internet, because all the long distance communication happens through fiber, and central to that is a laser. And to understand laser, we have to understand the low dimensional properties. All right. So another example here. Why are the low dimension systems important? In a way, this sort of also motivates why nanophotonics is important, right? This is all nanoscale phenomena. So if you look at any bulk semiconductor, You must have heard about that, and you have the valence and the conduction band. So conduction band, valence band. So they are all, there are bands of allowed states, right, in a regular semiconductor. But now, instead, if I look at a quantum dot, okay, that essentially is a confined structure. Instead of having a, one second. So yeah, sorry about the disturbance. This is I had to take the call. All right. So as I was saying, if you have a bulk semiconductor, you have the bands. But the moment you, let's say, make a quantum dot out of a semiconductor, let's say a 10 nanometer quantum dot, okay, as I have shown in the previous slides. If you have that, it turns out that the energy levels are no longer continuous, but you have discrete energy levels as shown in the picture here. So when you have such discrete energy levels, you can have emission at those different, for example, here, if I have, let's say, this level and this level, an electron can make a transition from the higher level to the lower level and emit light. Similarly, it can make a transition from this level to this level and emit light. And it turns out that the spacing between the energy levels is dictated by the size of the structure. Okay, we will talk a little bit more about it later in the week, this week, after a couple of lectures. But essentially, when you have these discrete levels, it turns out that they have very nice optoelectronic properties. And on the top here, you are seeing basically emission spectra of various quantum dots. Okay, and they have these very sharp lines. If you and if you look at even the bottom picture, you see that there are these colloidal quantum dots which exhibit a very wide range of bright colors. Okay, so they are very interesting applications of this low dimensional systems, and that is what we will be learning in this week. All right. Yeah, there is a question, I believe. Yeah.
So in the figure, you mentioned like 1s of E, 1s of 1p of E.
Okay.
What do you mean by that?
Well, this is essentially nomenclature talking about the type of bands. Okay. Here, what happens is a quantum dot, colloidal quantum dot as well. So I really don't want to get into that right now. But essentially, they have a 1s-like character. How is a s orbital? S orbital essentially means that electron is confined. It's the orbital looks spherical in shape. That means there's a probability of finding an electron in all 3 dimensions. But the moment you go to p orbital, it essentially means that electron can only exist in, let's say, a lobe on the top, a lobe on the bottom, and there are 3 different degenerate levels called as px, py, pz. Similarly, d has a different shape. So essentially, a quantum dot can work as an atom. It's a kind of a pseudo atom, right? Or similar to an atom. An atom is what? You have a nucleus and an electron tightly bound to the nucleus. Okay, but now you are trying to expand that. The size of the quantum dot is larger, of course, but then there are electrons which are confined to a certain volume. So it also has some similar properties as quantum dots, and yeah, it's interesting that way. In fact, when we talk about the quantum confinement, I'll talk about it. You can actually see that once you understand the confinement in 1 dimensions, if you go expand that into confinement in 3 dimensions, you get these orbitals, 1s, 2s, 2p, 3s, and so on, what you study in chemistry. They are actually solutions to problem of confining an electron in 3 dimensions. Okay, so we'll talk about it later on. All right, but right now, yeah, I just want you to remember that this is a very, very important and central idea, low dimension systems, and that's why we will spend the entire week on this. So in the next lecture, I'll start off with talking about absorption. Okay, because we talked briefly in the first week a little bit about when you're talking about the optical properties, but there's something more to it. We will actually understand the way to analytically approach that. We will introduce that for the bulk material first, and then we will talk about what changes when you go to a 2D material, or rather confined material in 1 dimension, right? Let's say quantum well, what changes, we will talk about it, and finally show you what happens if you confine it in one dimension, what happens. We'll show you that later in the week. Okay, so this will be an interesting week, and then we will move on from the next week. All right, yeah, thank you.